Today I'm going to show you an autonomous workflow where an AI agent detects an SLO breach using groundcover's MCP server, diagnoses the root cause from real eBPF traces, files a detailed ticket in Linear, and suggests a code fix. We're using Claude Code with groundcover MCP and Linear MCP connected as tools. First, let's create the problem. I have a simple order service deployed on Kubernetes. It's a fast API app with an intentional N+1 query bug. When orders have multiple line items, latency scales linearly because each item triggers sequential database lookups instead of batching them. I'm running a load generator at 2 requests per second for 60 seconds, and we can already see the result. 86 out of 120 requests have breached our 500 millisecond SLO. The cluster has now fresh trace data from this run. Now let's look at what groundcover captured on the logging side. Groundcover uses an eBPF sensor that runs at the kernel level on every node in the cluster. It automatically captures logs, traces, and metrics from every service without any code changes or SDK instrumentation. So everything you're seeing here was collected the moment we deployed the service. We're filtering by the SLO demo namespace, and you can see the application logs from the order service pod. These 200 OK entries correspond to the requests our load generator sent. If I drill into one of these log entries, groundcover automatically enriches it with context. The context tab is where it gets really interesting. You can see the container resource utilization, CPU, and memory for the order service pod, with the defined limits and requests overlaid. And below that, there's the noisy neighbors section showing what else is running on the same node and how much they're consuming. Then let's move to the traces view and search for the order service. The dashboard surfaces the golden signals, including a clear spike in latency that aligns with the load test we just ran. In the trace list, you can see the pattern. The health check and catalog endpoints are all responding in 1 to 2 milliseconds, but our orders endpoint is taking about 2 seconds. And these are all 200 OK responses. The service isn't failing, it's just slow, and that's exactly the N+1 pattern that the agent is identifying. Now we can select a high latency trace to inspect the individual spans in detail and click through the attributes, logs, and context tabs to view the exact request parameters and resource utilization during the slowdown. Now I tell the agent to run the detection workflow. The first thing it does is call groundcover via MCP. It's asking for workloads in the SLO demo namespace and sorting them by P99 latency. Groundcover comes back with the data, and the agent immediately identifies the breach. Order service P99 is about 3.8 times over our 500 millisecond target. No dashboards, no manual queries. The agent found it by talking directly to groundcover. It proceeds to diagnose the problem, analyze trace data and logs to confirm the root cause of the latency issues. Once the diagnosis is complete, the agent automatically creates a ticket and proposes a code patch. It presents a detailed comparison between the current sequential logic and a parallel implementation using asyncio to significantly improve performance.